today is sort of why we're building all these big radio telescopes and trying to map the universe, as if it's not intrinsically interesting enough. And then what the characteristics of these big radio telescopes are, how we need to build them, why we build them in a particular way. And then, I'll just show you the obligatory pretty pictures, but mostly of not the universe, but telescopes. But like I said, if you have questions along the way, please feel free to interrupt me. I'm happy to answer them. So mapping the universe with radio telescopes. Why mapping the universe? Why radio telescopes? So here is a very, very, very basic version of cosmic history. The whole history of the universe compressed into 2 different colors and less than a sentence of text. Nowadays, we see lots of galaxies out there when we look in the universe. So past our own galaxy, there are hundreds of millions of others. We are slowly but surely mapping them all out, their positions on the sky, how far away they are from us. We measure their redshift, and also other things about the galaxies, what sort of type of galaxy they are, how much star formation they're doing, what the mass of stars, the total stellar mass of those galaxies, and we can learn all sorts of useful and interesting things about how galaxies formed and subsequently evolved in our universe, our expanding universe, by doing this mapping exercise. So many cosmologists are kept entertained just purely by looking at galaxies that have as they've existed over the last few billion years. Before then, very close to the start of what we call the start of the universe, the Big Bang, which is, sometimes you're encouraged to think of this as some singularity of space-time. We don't really think there was a space-time singularity of that kind now. We had some complicated process called inflation that happened, and we don't really know fully what happened before inflation, but there was some reasonably early moment of time that sort of looks a bit like a Big Bang, and we can say that the origins of the universe we observe and see today came from that. Let's just call it the Big Bang for short. After that, the universe was extremely hot, extremely dense, and as it expanded, it cooled. As it cooled, all of that hot gas that was inside the universe slowly started to become neutral. The hydrogen ions recombined or combined with the electrons became neutral, and all of a sudden radiation was allowed to essentially travel through the universe unimpeded for the first time ever. Before that, the universe was filled with a plasma, radiation couldn't get through. So the first photons that we observe, they've kept traveling since then. We call that the cosmic microwave background, because those photons have been stretched by cosmic expansion, they've been redshifted, and now we don't see them. They were originally sort of in the optical and UV, now we see them in the microwave, so gigahertz, hundreds of gigahertz, that sort of frequency. We have really good maps of that radiation over the last few decades. Many people, including many people at Manchester, actually have done tons of work of making beautiful maps of that early radiation. So we know lots about the very early universe, a few 100,000 years after this thing we call the Big Bang, and we actually know quite a lot about what I'll call the late universe, when most of the normal galaxies that we see are observed. But you may notice a suggestive dark patch in the middle, and that's what I'm going to talk about today. So there's this period of cosmic history that we don't actually know that much about. We can sort of theorize, we can use the physics that we know to sort of project back from the galaxies we see today, or project forward from the cosmic microwave background and figure out what it could look like back then, but directly observing it is something else. So that's what me and many other people are trying to do, observe this directly for the first time. And now I'm going to move away from this simplified picture of just a dark patch that we don't know much about and sort of divide it up semi-arbitrarily into some different epochs of this early phase of the universe. And I think the one with the best name so far is the Dark Ages. Why the Dark Ages? So this is a period after the cosmic microwave background has sort of been let loose, when there are no stars or galaxies yet, no structures have formed. This is still very early in the universe's history. So no stars, no galaxies. That doesn't mean there's absolutely no radiation, no emission of light. There was the cosmic microwave background photons. There's other warm stuff that glows. I mean, but it's pretty dark. the normal glowing things that we as astronomers would like to see don't exist yet. So we call that the Dark Ages. The universe is relatively cold. It's cooled down a lot since that early phase after the Big Bang. And guess what? It's dark. Okay. After that, another evocative name, cosmic dawn. This is when the first stars and galaxies light up. Okay, the very first ones. So there was a period of the universe's history where there weren't any stars, and somewhere was the first one. I mean, we have no idea where, and we'll never see it. But there was a period of the universe's history where the first handful of stars, and they would have been very weird stars. Okay, this is a time of the universe's history where essentially you just have hydrogen, almost pure hydrogen gas with some fraction of helium, and practically no other elements available. Most stars that we see today have what astronomers call some amount of metallicity. So because we're astronomers, we like abusing terms, and we call anything that isn't hydrogen or helium a metal. So anything above helium is a metal. There wasn't much metal around at these very early times because many of those metals are formed by stars in things like supernova explosions or fusion within their cores. None of that had happened yet. So these first few stars are really weird because they're just pretty much just hydrogen stars. And that meant they were very large. They sort of glowed very brightly, and that meant they went supernova very quickly. So we call these population 3 stars. So again, astronomers and terminology, the first generation of stars are called population 3, and the most recent generation are called population 1. I'll have some words with my colleagues, please. And this was cosmic dawn. Okay, we'd love to know more about cosmic dawn, because within this period, how these first stars and galaxies lit up sort of set the stage for the rest of galaxy evolution. All the galaxies we see today are the result of several cycles of star formation. Stars forming, either going supernova or throwing off their sort of outer layers as planetary nebulae and stuff like that, distributing these metals throughout the sort of nearby patch of the universe, which are then absorbed as new stars form from collapsing gas clouds again. So much of the non-hydrogen stuff in your body has spent quite a while being formed in the middle of a star at some point. Certainly things like carbon, nitrogen, oxygen, they're just formed through normal stellar core fusion. Heavier elements tend to be formed, like iron, for example, tend to be formed in supernova. Most of the stuff you can see right now has been through 1, maybe 2, perhaps even more cycles of going into a star, being processed a bit, getting flung out of a star. So there's lots of violence in our history, lots of violent explosions and stuff like that. But cosmic dawn is this sort of interesting time when the very first of these objects that we're used to seeing in astronomy were forming. And the things we see there, they should be weird. They're the first ones. They have different chemical compositions to the galaxies and stars we see today. They're very hard to see. After that, we have reionization. So the universe was ionized because it was super hot. It expanded, the CMB formed, all these stars formed. Stars produce a lot of ionizing radiation of their own, especially very high mass stars. And they throw out all of these ionizing photons, essentially. So all that neutral gas that was hanging around since the cosmic microwave background was released gets ionized again. And so what happens there is we had that nice transition very early on from a completely opaque universe to a completely transparent one. Does it turn opaque again? Well, no, because these things, the universe has expanded a lot. This ionized gas is much more diffuse than it was early on, but it still gets ionized. And so much of the hydrogen, for example, that's out there isn't in a neutral form anymore. It's been ionized. So lots of ions, electrons, protons floating around out there because of this ionizing radiation from star formation. And that pretty much takes us, so this period from cosmic dawn to when all the surrounding gas that was neutral for a while is ionized again. After that, once it's finished being ionized again, we call that the late universe. So most stars, galaxies, things like that, sort of look like they do today after that point, to a reasonable approximation. And that's this what I'll call it the galaxy era. This actually covers over 10 billion years of, so that's billion with a B, years of cosmic history. Most of the universe's history, as we know it, was this phase of normal galaxies. Now, these galaxies do stuff. They evolve, they merge, they grow. They have active galactic nuclei in them that's pushing out lots of ionized gas as well. Black holes form, more stars form, very many cycles of star formation. There's lots going on during this period, of course, but it's sort of been going on in a similar-ish way for the past 10 billion years or more. So we want to see this blank patch in our timeline. We know lots about this late universe and how galaxies work. We know lots about the very early universe and the cosmic microwave background. But what about that middle bit where really the stage is being set for everything else? Those first stars, those first galaxies, the bit before, what caused those first stars and galaxies to form? And subsequently, how did they form? How did this reionization process happen? What type of stars caused reionization? Was it just really big, bright stars? Was it X-ray binary stars? They form very frequently in the early universe too. We have many, many questions, both sort of prosaic and very technical. What were the parameters of all these models? What type of gas? What was the exact mix of different types of metals? We have many, many questions, and they're very hard to answer because this is a period of time that's very hard to observe. It's so far in the past. There were hardly any sources that were luminous. I mean, how can you sort of observe galaxies if there are no galaxies yet? What do you observe? You need something to observe. And what I'm going to be talking about is observing radio emission that thankfully, and this is a real savior for us, comes from neutral hydrogen gas. There's a lot of hydrogen gas in the universe. At these times, most of it was neutral before reionization. And very helpfully, it emits at a wavelength of about 21 centimeters, so deep in the radio, which means as the universe has expanded, the wavelength of this has expanded to longer and longer wavelengths. That's a part of the EM spectrum that doesn't easily get absorbed by other gas and dust and things like that. If this was in the optical part of the spectrum, much of it would have been absorbed by now and we'd see nothing. So thankfully, neutral hydrogen gas gives off some emission at this wavelength of 21 centimeters, so we can actually consider trying to map out this very early phase of cosmic history. What do you need to do that? And that's what I'll talk about now. A really big radio receiver is the short answer. So I've already mentioned, so we see this neutral hydrogen gas. It's emitted at a wavelength of 21 centimeters, and then depending on how long ago, how far away it was emitted, it's then been traveling through the universe as the universe expands and therefore stretched. Its wavelength increases, it's redshifted. And depending on when it was emitted, the redshift will be greater the further in the past it was emitted. So if we can observe this gas, this sort of emission line from hydrogen, but see which frequency it's been redshifted to, we can tell how long ago it was emitted. So that's what we're trying to do. And of course, we know there wasn't just one moment where there was lots of neutral hydrogen gas and then nothing. It was over many, many moments. And so we want to tune into many, many frequencies at the same time. And each frequency will correspond to a different time from today, when that gas was emitted. And so we can sort of build up a picture of how much of this radiation was emitted as a function of redshift and therefore time. And that's what we're trying to do. So we don't just have a big radio receiver and tune it into radio 1, right? We're observing many, many frequencies at once, all at the same time, and measuring the brightness of the emission at all of those frequencies. So number 1, really big radio receiver. What I'm showing you here is actually this very curious looking contraption, which I promise you is a highly optimized cutting edge machine. This is called the Vivaldi feed of a telescope I work on called HERA. You'll see more pictures of HERA in a bit. That's the Hydrogen Epoch of Reionization Array. Acronym points. And what you see here is essentially the receiving element. This is, below that you can see these sort of funny dish type structures here. Those are just normal radio dishes. They are focusing the radio waves. They're about 14 meters across each, 14 meters in diameter. They're focusing the radio waves onto this strange contraption, and this is essentially a dipole antenna with various funny notches and bumps in it. That means it's very good at seeing radio waves across a broad range of frequencies. So if you just had a sort of bit of wire of about this length, that would pick up these radio waves, but it would be way more efficient at picking up these radio waves if they have a wavelength of 4 times this length than others. These are resonant antennas, and I'll defer to your EM courses or something before I go into details. But you know, you have a dipole antenna that has this property. That's not a desirable property. You'd like to see all of the frequencies about as well as all the others. It doesn't help you to measure one frequency really, really well and the rest kind of in a crappy way. You need a nice, what we call a nice flat band pass. And what that means is being able to tune into all these frequencies at once, roughly equally as well as one another. And so the reason you get weird shapes like this is because someone has taken some EM modeling software and burnt a lot of CPU hours of simulating shapes like this and deciding exactly how big these holes should be in the bottom and why it should be this weird teardrop shape all stuck together. And it works super well. It works super well. So this is called a Vivaldi feed, and it's sort of, like I said, reasonably cutting edge. I should probably say how big this is. This is sort of my height. It might not look it in this photo, but like if I put this next to me, it'd be sort of similar height to me. Ideally, you'd have a big dish. And I've shown you a picture of the biggest dish, not our pet big dish, which is merely the 3rd biggest steerable dish at Jodrell Bank. You've seen so many pictures of that, you'll be sick of them. I can never get sick of the Lovell telescope, actually. It's beautiful. But this is the biggest at the minute. This is called FAST, the 500-meter aperture spherical telescope. It has essentially been built in an entire valley in China. As you can see, a very beautiful valley that we've now spoiled with this giant radio eye with a very reflective metal surface. The bigger the dish you have, you get 2 advantages from a big dish. One is you're more sensitive. You collect more radio photons. We're looking at emission from, you know, a few million years after the beginning of the universe. It's been stretched and expanded out in such a gigantic way that it's super faint now. We're looking for something incredibly faint. We're looking for a signal that, if we talk about temperature units, it's in millikelvin. That's how bright it is, compared to typical radio waves at these frequencies, which are tens of Kelvin from a lot of things we see. So it's very faint. So we need a lot of collecting area, otherwise we won't see it. We won't have the sensitivity. A bigger dish also means, think back to some diffraction theory, sharper images, higher resolution. And so depending on how you want to map out your very early universe, what sort of level of definition you want to achieve in your maps, a bigger dish means you'll achieve a higher resolution. Now, as you can imagine, building a 500-meter aperture telescope in a really gigantic valley is quite expensive and disruptive to the local population and wildlife, and, you know, it's stressful too. There are better ways. So instead of building these giants, and these giants have a role, but for the kind of things we're doing, instead of building these giants, we build arrays of smaller telescopes which can achieve the same properties in terms of resolution and collecting area, but without having to wipe out an entire valley and replace it with metal sheets. So this is Hera again. Again, you can see these things, these dishes, they're actually made out of chicken wire. So the type of metal mesh that you'd use on a farm to keep your chickens from, well, keep the foxes out. Let's put it that way. why can we use such sort of basic material? Because these radio waves that we're looking at are sort of 2-3 meters in wavelength. They're pretty long wavelength, so they don't see the holes in this mesh. You can get away with a much cheaper, much lighter material than those metal sheets at these frequencies. You can do it with bits of wire, even. And that's great, because it's cheaper, and funding agencies like funding things that aren't too expensive. Well, I think they like funding things, if you ask them very nicely. Other ways in which this is cheap and low-tech. These are just telegraph poles holding it up. Just the normal kind that you'd see on the street, the BT ones or something. They're perfectly strong enough, and they're also very cheap. And between them, it's kind of hard to see in this photo, perhaps, but the shape of this dish is being provided by polytube, you know, the tube that sort of plumbers use for your outside drains. It's just been held up by that. It turns out to be flexible in the right way and strong enough. So each of these dishes, even though it's 14 meters across, I mean, that's, well, maybe even just a bit bigger than this lecture theatre. They're reasonably cheap to build the dish itself. We spend most of our money on computing, which I'll talk about in a bit, and people. People are very expensive because they insist on eating and stuff. So very expensive, those people. This array, Hera, is a constant work in progress. We can operate it with just a few dishes, but we're trying to build it out to a total of 350 dishes, which is quite gigantic. 350 times 14-meter dishes spread across this patch of desert here. So you can imagine, if we'd use more expensive materials, you know, we'd need a couple of captive billionaires to provide that sort of money for us. As it is, we're sort of in the tens of millions of dollars bracket of experiment. It is in dollars. This is a US-led collaboration we're part of. So that's Hera. How does this all work? Well, I'll show you in a second. I just wanted to show you another type of array. We call these arrays of dishes with a different design. This is the CHIME telescope in British Columbia in Canada. And essentially, instead of individual dishes, they've been very clever and stuck all their dishes together as these big sort of half pipes. And their receivers aren't these Vivaldi feeds that I showed you earlier. They're this row, that white metal thing on top that has individual receivers hanging from it. And there are many of them. And so this is a way of getting quite a large collecting area, but without having to build a giant dish and being able to stick lots of your receivers together. It turns out it does have pros and cons. One of the cons is it's only half a dish. It's only focusing the light in this direction. Along this direction, there's no focusing of the light. So it sees a small strip of sky in this direction and the whole sky in that direction. So that's a bit of a trade-off. It's seeing a stripe of the sky rather than a patch. So how does this work in technical terms? We're doing interferometry. So instead of having one giant dish, and we sort of let that measure the amount of radiation that's coming in, we take all these individual dishes and combine the signals from every pair. So if we have 100 dishes, how many pairs do we have? We have 100 times 99 divided by 2 unique pairs. Why divided by 2? Because A paired with B is the same as B paired with A. So you have many, many, many pairs for a given number of antennas. So I'll let you do the maths on 350 antennas, how many pairs we have. But we combine the signals from every pair. And that means we have lots of data coming in, much more than just a single big telescope. We need a tremendously high data processing rate. So you've probably come across the square kilometre array by now, and people have talked about how, the square kilometre array generates about 2 internets worth of data per day, which is true. It does at its raw data rate. These interferometers are really pushing the limits of how fast we can process data with modern technology. For something like Hera, our specs aren't quite as difficult as the SKA, but we still have literally a shipping container full of graphical processing units, GPUs, out in the desert next to it that's doing all the maths needed to combine these signals. So somewhere out in the desert, Hera is in the Karoo Desert in South Africa. There's just the shipping container, one of the 21-foot ones, just full of GPUs, melting away because they get very hot doing this as well. I think I might have a picture of that actually. Yeah, okay. There's my colleague Zaki fiddling with something. I can't. He's fiddling with one of the boards that converts the data coming in and turns it into digital. So he's in one of these shipping containers in his sun hat, despite the fact that it's dark in there, with all these racks and racks and racks of this equipment. Because we're taking this data from 350 individual dishes. This was an earlier photo actually, so it's not quite 350 yet. We have all these cables coming in. You can see tons of them there on the left coming in. They're going into these very specialized computers, which their job all day, every day, is to just multiply numbers together as fast as humanly possible, or not humanly possible, as fast as computerly possible, which is quite fast. And eventually dumping that out onto a disk for people like myself and my research group to analyze. Why is it doing all this? Why do interferometers work this way? They multiply the individual voltage signals from each dish together for every frequency. They do this very fast, so for many, many individual time samples, for different polarizations as well. And in doing this, when you start averaging over things in the right way, you get a nice coherent fringe pattern like you would with an optical interferometer, and you can measure the amplitude of that fringe pattern. And you can measure this as a function of frequency and stuff like that. And using that, I'll spare you the maths in this talk, but come and chat to me or go to the radio astronomy course if you want to learn more. You can essentially convert that back into an image if that's what you're trying to do. So it's all big computing as well. The last thing you need, or really need, is to be as far away from people as you possibly can get. There are many reasons for this. People are cruel, but that's not the reason. The real reason is people generate lots of radio emission. I mean, not just me standing here, it's the devices that people use. Obviously, mobile phones, computers, Wi-Fi, internet, cell phone coverage, all of that sort of stuff generates much brighter radio waves. Of course they're brighter, we're trying to transmit data across some distance, much brighter ones than any of the signals we're looking at on the sky. And they swamp these detectors. These are incredibly sensitive detectors. These are things for trying to detect minuscule amounts of radiation from just after the Big Bang. And then you put your mobile phone next to it. I mean, that doesn't work out well. We have all these big filters. So most of these things like mobile phones and Wi-Fi, they only operate over a narrow frequency range. And so we can put a filter in here that sort of cancels out most of that brightness, so we can observe the stuff around it. It means we're missing a chunk of the data, which means, if we're missing a chunk of frequencies, that means we're missing a chunk of cosmic history. So the bigger the frequency range you have to chop out because of 5G or something, the more of the universe we're losing. And of course, someone's going to invent 6G soon, aren't they? And then we'll lose an even bigger chunk. And then 7G, well, that'll make me really mad. Especially because my phone reception is terrible where I live. So, every new class of device, every new type of transmitter, people are hacking away at the available EM spectrum, the radio spectrum that we are trying to measure. Now, fortunately, at these frequencies, it's mostly not mobile phones or anything like that anymore. We have the most problems with FM radio. So the frequency range that Hera covers is about 50 megahertz to 220 megahertz. FM radio is 88 to 108 megahertz. So, Radio 1 kills out, like 10 million years of cosmic history or something. So I don't know if they know that, but they do. So we'll never be able to observe that because there's just too much bright emission from humans in the way. Other things too. So a really important one nowadays is communications and global positioning satellites. They're very bright too, again, for obvious reasons. You want to be able to see the signal so you can, drive your car into a river or something. That's whatever you're trying to do. And, they're super bright and with human-generated emission, you can get as far away as you like from humans. I mean, go to a big desert and reduce it a lot. It's still quite long-range emission, but you can reduce it a lot. That's why we go to deserts. But for things from satellites, you can't escape them. Not really. The satellites are always there going overhead. Now, there are some fun things with this radio interference. So because we're looking at such faint stuff, we have to worry about interference much more than your normal radio astronomers who are just looking at galaxies or things like that. We see some really weird stuff. So a big form of interference that we see out here in the desert is from cows getting zapped by electric fences. When they get zapped, we get a little pulse of radio emission. So, you know, we can tell if the cows are having a good time or not based on how bad our data quality is. Another weird one is, so we're very far away from the nearest settlements in this place. This is actually on the site of where half of the square kilometre array will be built. So it's a very radio quiet site as far as it goes. The nearest town's, you know, tens of kilometres away. But planes fly over and they reflect the emission from over the horizon. And so now and again we just get a brief burst of FM radio or something like that that's been Doppler shifted because the planes are moving quite fast. And so the first time you see that it's weird, and then now we're just used to it. Other things that cause radio emission. So lightning is terrible. Lightning. So you know, this is a part of the world where you do get lightning storms off on the horizon. Some types of human-generated radio emission, or most types, like I said, are narrow band, so they only work on a narrow range of frequencies. Lightning is essentially, you know, an electric spark in the air. That gives you broadband radio emission. It goes all the way across all of your frequencies and is very bright because it's nearby. So when there's a lightning storm, we see it very, very definitively. There are some other fun ones that don't apply to us at Hera, but other radio telescopes have had these issues. So one of them is windmills. So there's a big radio telescope called LOFAR in the Netherlands, and they saw this weird varying signal. I go up and down, and essentially over the horizon, out in the sea, there are some wind turbines rotating. And depending on the direction of the wind and how windy it is, they'd be rotating at different rates and reflecting radio waves off their blades back towards the telescope. And so you see this weird pulsing signal, which if you aren't skeptical enough, you would claim was aliens, but actually it's windmills. I think we had another good one a few years back as well, which was someone's ready meal. Essentially one of the telescopes in Australia, they saw this weird bright pulse around sort of most days, like between sort of 12-ish and 1-ish, there'd just be this bright pulse. And so, oh, that's weird. Maybe there's some, like the diurnal rotation, like maybe there's something reflecting from a satellite or something. No, it was the microwave in the tea room that was you know, someone was opening it and it wasn't, you know, it was letting out some microwave emission that was very bright. They were briefly called peritons. I'm not sure why, but if you ever go out to Jodrell Bank and go in our tea room, you'll see our microwave is in a Faraday cage to prevent such things happening. So essentially everything is against you as a radio astronomer because everything generates radio interference. You know, you name it. So getting as far away from people as possible helps, but it doesn't solve the whole problem because, again, people insist on putting things in orbit or flying planes over. So what does the telescope actually see? So I've been telling you about, there's this faint radiation from very early in the universe's history. What we actually see is where the neutral hydrogen is, which is where the ionizing radiation isn't. So if you have the first stars and galaxies, they switch on, they start producing UV photons, which can ionize neutral hydrogen. When the neutral hydrogen gets ionized, it's not neutral anymore. It can't give off this 21 centimeter radiation, and so we don't see it in the radio anymore. So what we see is essentially the bits that haven't been ionized yet. We see the bits around the first stars and galaxies. As soon as you get one of the first stars and galaxies, you get a big hole in your map. And that's what I'm showing you here. So this is from a simulation, actually. We haven't observed it yet because it's so hard. But these bright patches are sort of where we get lots of emission. That's where the remaining neutral gas is from this process. But as soon as these things start ionizing, the intergalactic medium around them, you can't see anymore. So we are hole finders. The way this works with big dishes versus interferometers as well is a little bit subtle. So with a single dish, you're essentially just, you make it as big as possible, and what you see is essentially just a single pixel on the sky, and then you try and build up an image from many such pixels. If you can't move your dish, you just let the sky rotate over you, and that's fine too. But you're trying to build up an image pixel by pixel. With an interferometer, it doesn't work that way. What you're measuring is this interferometric fringe pattern, and a better description of what these things see is each pair of dishes, each pair of receivers, sees an individual Fourier mode of the emission on the sky. So rather than being sensitive to individual pixels on the sky and building up an image that way, it's like you're measuring each Fourier mode one by one, and then you can do a big inverse Fourier transform and hopefully get the image back that you were hoping to see. The further apart your dishes are, the finer the detail you see, and the closer they are, the coarser the detail you see. So you need a mix, because if you didn't have any of the short distances, the short baselines, you wouldn't see the large-scale emission. You'd have no way of seeing it. You wouldn't observe those Fourier modes. And vice versa, if you didn't have any dishes far apart, you wouldn't see the fine detail. So it's a bit weird and subtle. You're essentially trying to build up an image from its constituent modes, and you might be missing some of them. So you have to be very careful with how you design these arrays if you do want to get an image out of it at the end. And then the next thing is we're observing this as a function of frequency, and as I've said, each radio frequency corresponds to a different amount of redshifting of the 21 centimeter line. So each frequency is sort of a different slice through the universe at a particular cosmic time. And so what we do is we just build up this image or set of interferometric measurements that we can turn into an image as a function of frequency, which gives us a 3D map. But it's not any 3D map, it's a 3D map showing us how things have evolved in time. Now, we're not looking at the same object evolving in time. It's not a movie in that sense. Each object that we see is a different object observed at a different time. So, that's just the way light travel works, I guess. If we wait long enough, we can see the same object as it was. If I wait 10 years and observe the same object again, I'll see what it looked like 10 years later. We don't have time for that. Some people do, but that's not what we're trying to do. We're trying to make this kind of strange 3D map where we're not making a 3D map, a movie, as it were. We're making this thing that we would say is a sort of map on our past light cone. So if that's a bit subtle, you're right. Come and chat to me after if you want me to draw some mad diagrams on the board. But as it is, that what we're sort of seeing is something a bit movie-ish. There's a time bit, but also a space bit too. So it's this sort of strange sort of map that's telling us what's changing with time, particularly the number and size of these ionization bubbles. Right, as the ionizing radiation moves out from the first stars and galaxies, it's going to take out more and more neutral hydrogen. And so by looking at that, we can see how intense these initial processes were, how many of the first stars and galaxies there were, how fast they formed. We can even, depending on the amount of energy that they're kicking out, try and figure out what type of process was responsible. Is it just these population 3 stars, that are very massive hydrogen-only stars? Or is it X-ray binaries, sort of much smaller stars orbiting each other and giving off lots of X-rays? Is it something more exotic? Is it things like dark matter annihilations, putting energy into the intergalactic medium? We can tell the difference between all of those things if only we can count the number and size of these bubbles as they change over cosmic time. This is quite a nice simulation that a colleague of mine made that looks much prettier than any of the ones I've shown you so far. And those bright edges there, what you're seeing is an ionization front. So the pale blue regions are supposed to be sort of pockets of the universe where ionizing photons have come out from these yellow things, these ionizing sources, and then the edge of those, as you get this very sharply defined ionization front. So these bubbles have, quite a particular shape. If you were to do a cross-section of them, they're very sharp edges that you see. And again, you can tell things from the shape of those and how deep they are and all of that stuff. There's obviously a lot of astrophysics here, if only we can make maps like this. So I'm just going to finish off now by showing you a few bits and bobs of different telescopes I'm working on and sort of giving you a sense of what's in the future. So this is essentially baby photos of Hera while we were in the middle of building it. So in the background, so this is the Karoo Desert. It's sort of a very arid semi-desert, sort of 8 hours northeast of Cape Town in South Africa. It's nice and flat, which is always good. There are scorpions. We had bees recently. Like, we couldn't go out to the telescope because there were like a swarm of bees had decided to hang out there. And I remember distinctly having one meeting where we were just discussing how many bee suits to buy. Like you don't sign up for that with a physics degree, do you? Like, oh, how many bee suits do we need this week? Fortunately, the bees moved on. But, because you're out in the wilderness, there is stuff like that. Other telescopes have had issues with... I was listening to a talk earlier today, actually, a telescope in Western Australia, where there are camels for historical reasons. The camels have been moving boulders. It's been causing the sand to sort of flow towards the boulders, and like some of their instruments are like on a tilt now because the camels move the boulders. Like, how are you supposed to prepare for that? Like, I don't know. But lots of stuff like that happens when you're out there in the elements. I have some other colleagues who have a radio telescope, a very small one that they built on this super remote island in the South Atlantic, which, again, due to historical reasons, possibly involving British sailors in the 1800s, is infested with rats. And the rats eat the cables, and they've had to do multiple layers of wire mesh to prevent the rats from eating the cables, but the rats can still get in because they're very clever rats. And, like there's a lot of this. I spend a lot more of my time worrying about nonsense than I ever thought. But it's all good fun. So here's the Hera site out in the Karoo. In the background, you can see some sort of white dishes. Those are dishes from a telescope called the Meerkat array, which is a precursor to the square kilometre array and will actually become part of the square kilometre array. They're just going to plug it in. It's a USB-C connector, and we just hope that you have to rotate it twice until it goes. No, it's much more than that, but Meerkat's a beautiful array that works extremely well, and we use it for lots of similar things to this as well. I'm just not going to talk about it much today, but sort of in the foreground there is this strange sort of squished together array of these 14-metre dishes made out of chicken wire, which is Hera. By the way, the locals were not happy with us about the chicken wire thing because we bought out like the whole stock for that region. Like, the farmers couldn't get chicken wire for a couple of months, and so yeah, we were not good neighbours on that count. But it's fine now. We've stopped buying chicken wire. We've got all we need. If you know anyone, though, let me know. So this is Hera at sort of mid-construction. It's now fully built to about 350 dishes, which are all connected together and via this shipping container full of GPUs that is currently offline because one of the power switches melted. I mean, there's loads of stuff like that. So this is another view of Hera since it's been slightly more built out, and you can see how close together these things are. Yeah?
Sorry, on the previous slide,
yeah.
There were some telescopes like around the front. Is that like Is that because I know you said you need ones far away for the idea? Do you have like a concentric ring around the edge of extra telescopes?
Yes. So the way so that's a great question. So the way this is laid out is in a sort of split hexagonal pattern. So if you have circular dishes, the sort of optimal way of closely packing them together is a sort of hexagon. shape. And that's nice because you get pairs, so baselines, pairs of dishes at a range of different lengths, but many of those lengths are repeated. So you get many pairs of dishes that are the same distance apart, which means that increases your sensitivity because you're measuring the same thing multiple times, and so you can do an average, and you can measure it more sensitively. So the ones that are closely packed together are to measure big stuff on the sky, like these pockets of ionized blobs. And the ones that are further out are called outriggers. That's to provide us higher resolution images that we can use to image things that aren't this emission, things like bits and bobs from our own galaxy or galaxies closer to us, and remove it. So they're sort of there as a way to help us clean out all the stuff we're not interested in our data, and hopefully get to the super faint stuff that we do care about.
Would that include like brown dwarfs, for example?
Yeah, they're not a massive contribution to what we see at these frequencies. They're mostly the ones we can see or would be able to see. They're concentrated around the galactic plane, which is so bright in the radio anyway, we just don't observe it. Like trying to look through the galactic plane at these frequencies it may even be impossible. There's a lot of ionized gas in there as well. So in principle, we'd be able to see them, but in reality, we avoid those areas. We're looking outside the galactic plane where our job is fractionally easier. Yep, good question though. So yeah, this is just another shot of the galaxy from far away and to the side. The array. And then this is the satellite view. Thank you, Google, for spying on us constantly and providing this beautiful image. So this is what I mean by a split hexagonal layout. So everything's almost hexagonal, but then we have these splits in the middle, and the reason for that is it just gives you a few extra different lengths of baseline that helps us optimize for the signals we're trying to see. So it's maybe a bit hard to see, but in the sort of lower left, you can see these buildings next to it. That's where the shipping container is, and it's hard. I mean, you can't see on this image, but the ground is covered in cables running from these things into that shipping container. No antelope or anything that I can see on here, sadly, but there's quite a bit of wildlife out there too. I have some other colleagues who they get sheep headbutting their dishes. What can you do? So like I've said, our own galaxy is bright and in the way. So this is a picture of our own galaxy in, it's called synchrotron emission. So very high energy electrons spiraling around magnetic fields give off bright radio emission at just the frequencies we care about. It looks beautiful, but it's in the way. So we try and avoid looking directly through the middle of the galaxy, but we still need to subtract it. It's something like 10 to the 4 or 10 to the 5 times brighter than what we're trying to observe. That's a fun problem. If you're into statistics or data science, it's a good data science problem. And like I've said, humans, always a problem in many ways, but in this particular way, they are cutting out chunks of our band. So this is actually from the Meerkat telescope, not Hera. Excuse me. So this is at higher frequencies, but that's in the Karoo Desert too. And these spikes are not from the universe, they are from the humans, even hundreds of kilometers away. And you see it's quite nasty, so we lose big chunks of cosmic time that we can't observe. This is varying in time as well, so it's not just a spike there and, oh, avoid it. It's going up and down and all sorts of weird things. So this has a particularly difficult interaction with a type of telescope where we're not trying to map this 21 centimeter redshifted radiation. We're just trying to measure its average temperature as a function of cosmic time, because that has interesting information about how galaxies evolved and stuff like that as well. These are called global signal experiments. The one on the left is called EDGES. That's this weird table thing. I can tell you about why it's a weird table another day, perhaps. This is trying to observe this average signal instead, and so the fact that humans are in the way is Not helpful, because rather than making a map that maybe you can cut bits out of when the radio emission from humans is a problem, you lose everything for a little bit when you're doing this sort of experiment. This is the beginnings of our own attempt at measuring this at Jodrell. So this is a horn antenna called Rhino. That's a Manchester-based experiment. And we're building a 5:1 scale model of that at the minute. That's what this strange mesh contraption is. We need to build one that's about 15 meters tall shortly, and we just secured some funding to help with that. So watch this space, or maybe not. I'll get squished by a telegraph pole or something, and that'll be on the news. But we're trying to build one of these things to measure this emission and freeze out as much of the human-generated emission as we can. So in the future, I've already mentioned the square kilometre array, but this is what we're moving towards. So this is a load of these that, if you see them up close, they sort of look like metal Christmas trees. Again, they've been super optimized to give you this flat bandpass to work well at a whole wide range of frequencies. And there's hundreds of thousands of these spread across the Western Australian deserts. That's sort of the next place that these things are going. So as you can imagine, many signals going back and forth, all these things are connected together, lots of computing needed to do the interferometer bit. That's sort of the future on the ground, but fundamentally it's still very hard to get away from the human-generated interference. And so the sort of end game of this whole field is building some of these things on the moon. Why the moon? And, well, particularly the far side of the moon, because it is the only place in the entire solar system that's always pointing away from the humans. Okay, so you go to Mars, it's rotating, you'll see the humans for a bit, but you go to the far side of the moon, because the moon is essentially tidally locked, it's always pointing away from the humans. And I include myself in that statement. It's always pointing away from me as well. So if you are willing to play the game of international geopolitics that results in many large nations trying to race one another to get to the moon and exploit its resources. If you're willing to ride on the coattails of those people, you can propose things like this far side array, which is essentially putting a lander on the far side of the moon, and so a little robot goes out of it and drops some of these antennas every few meters, and you can build an array out of that. So this is something that's sort of quite low-tech. These things have to be simple and lightweight. It costs about $1 million to put a kilogram of material on the moon at the minute. So it better be lightweight if you're putting a big array of things on there. And so once you've convinced NASA or someone to give you that $1 million per kilogram, you can put this thing up there and hopefully measure some of this radiation unimpeded by the humans until the humans move to the far side of the moon and establish moon bases or orbiting space stations, which they're trying to do already, which is very annoying. So we're in this unique part of human technological history where we've maybe got a 10-year window before the humans mess it up again. So I have a number of colleagues who are trying very hard to get stuff like this on the moon ASAP. So yeah, watch this space, but only for 10 years, because after that I think we're screwed. All right, that's everything from me. Thanks very much. So we have a few minutes for questions, if you like.
So does anyone have any questions? You can ask them now.
You can also email me about stuff, of course. But yeah, please go ahead.
In order to process the radio waves, what type of programming language do you use?
Yes. So the question is, what programming language do we use to do all this processing? The short answer is many different ones, depending on what we're doing. The very high data rate stuff is extremely specialized, and you have people using FPGAs, field programmable gate arrays, which are these sort of reconfigurable chips that are extremely fast. Or they're using GPU-based programming languages, which is things like CUDA. Those are the super fast things. What I do is a bit further down the pipeline. I'm analyzing the data, and we do most of that in Python. And we sort of do it on a sort of big high-performance computer because there's a very large volume of data, but we don't care as much about having the sheer amount of data running through and having everything down to nanosecond accuracy. What we're doing there is we care more about having something where we can write down the statistical problem in a nice user-friendly way so we don't make as many mistakes. And that means a high-level language like Python normally has some nice packages that help us with that.
Thank you.
No, no problem. Yeah?
Are you sort of interested in, are you using the data from the bubbles to look at star formation rates, or is there something else that you're looking at in particular?
So we're at a level where the star formation rate is very, very low. Well, up to a point that it becomes massive. So we're not at the point yet where we can actually image this. We're trying. Hera may be the first to detect this signal if we take another year or so of data. We should have the raw sensitivity to do it, but it's so faint that no one's done it yet. We only put upper limits on these processes. We can sort of tell you, well, the bubbles can't be this big, because we would have seen them already. They have to be this big or smaller, which does tell us something, but it's obviously not as exciting as seeing them sort of in the flesh, as it were. The SKA is designed to image them directly and have some nice maps of these things. You'll be able to tell things like, I mean, yeah, again, star formation rate's a difficult one at such early times because it's a very, what we call a shot noisy process. Star formation is very rare at a certain point. But after that, certainly. And you have other things like how many photons escape from around their galaxy without being absorbed, because the ones that escape can go and ionize stuff. So you have things like the escape fraction, the mean free path of the photons, the energy of the photons and stuff like that. So there's lots of astrophysics that you can learn and link back to our understanding of how galaxies respond while they're forming to things like having a load of high energy photons beamed at them. And there's a big role here for simulations, very big complex simulations that do a sort of full hydrodynamical treatment of how all these photons and gas and turbulence and all sorts of stuff is going around, which is very fun stuff, but measurements would help those become more realistic. Oh, it's so peaceful. You're always welcome to email me or even come and see me about any of this stuff. So this is all done within, or many of the things I've talked about are done within JBCA. We have quite a big group of people working on different aspects of this problem at both low and high redshifts. We're sort of gearing up for the square kilometre array ourselves. So you're always welcome to come and chat to us about that. Just drop us an email. Great, thanks very much. Oh, I should probably not steal the microphone. There you go. Thank you very much.
That was really good.
No, thanks for inviting me. It's fun. I'll have to run off to my next meeting.
There was a very cool coincidence. The lecture after this by the Chris Summit is also something about. I think it was on SKA.
Oh, good.
So it's a theme.
We're very big on SKA anyway, so you can't escape it from in Manchester.
What's your question?
Yeah.
For the lunar array, do you require or are you good just on the surface?
Some of them need a crater. So the problem with the far side of the moon is the temperature changes a lot between lunar day and lunar night. So some protection from that is very useful. And if you want to build a big dish, you can build that using a crater. This isn't that sort of experiment. It just spreads out these smaller things, but a bit of protection from the sun. There are many things that go into optimising.
Why not the poles? Because you don't want to see into the galaxy.
The problem with the poles is you can see the humans.
Yeah, that's true.
It has to be the far side. About 40% of the far side is quieter.
I see.
The moon is slightly transparent to these radio waves as well. So some few of the mission comes through the crust of the moon.
Wow.
Yeah, it's very annoying.
How does that come? Like for the waves to go through the moon?
So So very low frequencies. So some of these go down to 5 megahertz or so. The radio waves just aren't impeded by rock.
I mean, I know the particles was like regularly they're very ionized, but I didn't know that actually like radio waves would go to the entire surface of the moon.